Welcome to session 8 of electronic structure theory. In this session, we'll be talking about probably right now at least the gold standard for treating dynamical electron correlation. But of course, it's also the most expensive computationally. That is, its computational cost scales with very high powers of the number of atomic orbitals in our basis set. This is called coupled cluster theory. And in this theory, what we'll be doing is to talk about how the coupled cluster theory differs qualitatively from the way it expresses the wave function from configuration interaction, or MCSCF, or Møller-Plesset. It's a very different way of expressing our electronic wave function. And it was derived largely by comparing its fundamental underpinnings to what's called the Mayer and Mayer cluster expansion in statistical mechanics. It's a many-body expansion that describes how particles interact with one another. And so coupled cluster theory is enough different from CI, MCSCF, and Møller-Plesset that it deserves some special treatment. And in session 8, we'll be talking about the underpinnings of coupled cluster theory, its strengths, its weaknesses, and in particular how it scales to very high powers of the number of orbitals in our basis set. So that's what we'll do in session 8. Welcome to session 8 of electronic structure theory. Today, the subject is coupled cluster theory. And so we've talked about Hartree-Fock methodology, and we talked about MCSCF and configuration interaction and Møller-Plesset perturbation theory. And today, the other sort of mainstream methodology, coupled cluster theory, will be discussed. Now, some of you might wonder, where's density functional theory? Well, I've relegated that to a separate section, a couple of lectures down, just because it isn't easily discussed within the same framework as these other methodologies, because they share a lot of the same terminology and so forth. So I'm going to treat coupled cluster theory separately. The density functional theory separately. So coupled cluster theory. The one thing about coupled cluster theory that's especially difficult to explain is the way that you express the wave function is intrinsically a little bit different than in MCSCF and CI and Hartree-Fock. You do start out by saying that you have probably a single determinant. So most coupled cluster theory, people are working on improving it, but most coupled cluster theory that's used these days is predicated on a single Slater determinant starting point. So again, if you're not doing a problem that allows that to be reasonable, probably shouldn't use coupled cluster theory. But if you are doing a problem where a single Slater determinant is maybe reasonable, or at least you're willing to live with it, then here's how coupled cluster theory goes. It says, okay, you have this function phi, capital Phi, which is usually a single Slater determinant, and you've done some kind of Hartree-Fock calculation to get the spin orbitals to go into that determinant. And now what you do is you express the correct wave function, or at least your approximation to it, psi, not as a linear combination of Slater determinants formed from these Hartree-Fock spin orbitals times CI coefficients like you do in MCSCF or CI, but you instead express the wave function as an exponential of some operator t acting on this Slater determinant phi. And the operator t, you say, there's two components to this that I think should bother you. What is this exponential all about? And what's this operator t? Why not just express things in terms of a linear combination of determinants? Well, let me first explain what the operator t is. The operator t actually isn't all that intimidating, except it tends to get expressed in what we call second quantization language, which is just a way to say a framework in which you can describe promoting an electron from one orbital to another. So, for example, when I write this operator t as a summation over I and m of tim times m dagger I, what does that mean? Well, the I means destroy an electron in spin orbital phi I. The m dagger means put that electron instead into spin orbital phi m. So this is just a weird notation, second quantization it's called, for promoting an electron from orbital I to orbital m. So these generate single excitations, and TIM is just the analogous or the analog of the CI coefficient. So TIM is just the coupled cluster way of writing the coefficient. So if you were doing a coupled cluster calculation called CCS, single excitations, this T operator would only include this first term, the TIM, M dagger I, and that would generate, at least at first glance, something that would be single excitations with coefficients that are given by TIM. Now, there's two things that still have to be addressed. T includes usually more terms, and also it isn't just T that acts on the function phi to give psi, it's exponential of T. And we'll have to talk about the exponential in a minute. But let me just proceed a little bit further along with T. Sometimes you do calculations where you say, I'm going to do CCSD. That means couple cluster with single excitations, the first term here, and D, double excitations. So the sum that says sum over ij, m, and n of an amplitude or coefficient T sub ij super mn, that's just a coefficient, that's one of the unknowns, times this term, this m dagger, n dagger, ji. That just means destroy an electron in orbital I, destroy an electron or remove an electron from orbital j, and place them into orbitals m and n instead. This generates double excitations. So the bottom line is this kind of way of writing T in terms of single excited, doubly excited, maybe triple excited. If you did CCSDT, you're doing triple excitations too. That's just a couple cluster way of saying what level of excitation you're going to include in your calculation. Now we have to deal with this thing of, okay, if we just wrote psi as 1 plus T acting on phi, then the 1 times phi would just be our reference Slater determinant. The T acting on phi would give single and double excitations, whatever level you decide to put in your T operator. But there's more to it. The coupled cluster theory expresses the wave function not as 1 plus T acting on phi, but the exponential. Now what I want you to sort of in your mind be prepared for is, what's the exponential going to be about? Well, we know the exponential of T would be 1 plus T plus TT over 2 factorial plus TTT over 3 factorial plus etc. So the first two terms of exponential T shouldn't scare you, because that's just 1, the Hartree-Fock determinant, plus T phi, that gives your singles and doubles. But then the problem is, what's all this stuff about TT and TTT and so forth? Okay, so let's just talk about that just a little bit. And just as a pedagogical purpose, let's just consider, for example, that maybe you've decided in T to only put doubly excited terms. I just want to do this for pedagogical simplicity. So let's say that T includes only terms that are like m dagger, n dagger, ji, with the amplitude that goes with them. What would be then in exponential T acting on phi? Well, that would be 1 plus, our summation of T's times the double excitations, plus 1 over 2 factorial times a sum of T amplitudes, double excitations, times another sum of T amplitudes, double excitation, T squared. Plus, of course, 1/6 T times T times T acting on phi. Now, when you go through all this and you sort of just stand back and are not so afraid of it, you just say, what's in this wave function then? Well, the 1 times phi is your Hartree-Fock, like I said before. The T times phi is your double excitations that you're familiar with. But then let's talk about what's this TT and the T cubed acting on phi. Well, the TT, the first term in T would generate double excitations, but then you have another T acting. So in principle, that could generate quadruple excitations. And the TTT could generate 6-fold excitations. And you say, well, good, that's making higher and higher excitations, more and more determinants in my expansion. But the thing I want you to notice, though, is that in these, for example, quadruple excitations that would arise from T acting and T acting again on phi, the amplitude, that is the coefficient that the couple cluster theory wave function would assign to a quadruple excitation like that, would be a product of the amplitude that is describing a double excitation times a product, its product with another amplitude that is from another double excitation. So to say it another way, the coefficient of that quadruple excitation is not treated as a linearly independent separate parameter. It is assumed to be given by the amplitude of the double excitation times the amplitude of the other double excitation. That's the key thing about couple cluster theory. It does not assign to quadruples and 6-fold and 8-fold independent parameters as coefficients, so it keeps the number of coefficients down at just the number of double excitation coefficients. You say, is that crazy, or is that correct, or is it wrong, and how wrong is it, and so forth? Well, let me just reflect on that a little bit with a couple of things that you probably aren't familiar with, but I would hope one of them you would be familiar with. First of all, in the old days of electronic structure theory, people actually carried out CI calculations where they said, we know the first terms are double excitations. And then they said, let's do then triple excitations and quadruple excitations. And they did CI calculations that were single, double, triple, quadruple, and they noticed something. They noticed that the coefficients of the quadruple excitations in the CI calculation, even when they let those coefficients be independent parameters, were approximately equal to the products of the coefficients of the two double excitations that gave rise to that quadruple excitation. So they said, what does that mean? And then the people who were developing CI at the time, they were pretty well schooled in lots of other areas of theoretical chemistry. And one thing that came to mind to them was in statistical mechanics, and this is, I need a little digression now into something that's in statistical mechanics. In stat mech, they knew that when you're studying the theory of dense gases, the first thing that you do is you say an ideal gas has no interactions. So its partition function is just that normal 2 pi mkt over h squared to the 3 has v to the nth over n factorial. That's the translational partition function. But then Maria Goeppert-Meyer and her husband Joseph Meyer, they developed this so-called Meyer and Meyer cluster expansion that allowed you to put into the partition function some intermolecular potential contributions to the partition functions. And I'm going to walk you through this in a minute, but just let me tell you the bottom line. They noticed that in the partition function, the interaction potentials among the particles in a gas, as you start to compress it and go to a little higher and a little bit higher density where ideal gas law is no longer valid, the first corrections that were obtained to the ideal gas law were due to what are called binary collisions, individual encounters of two molecules in the gas at a time. That's like double excitations and analogous to CI. But then, now here's the take-home important lesson. The next most important term was not three-body collisions, because that would involve three particles being in the same region of space at the same time. Instead, the next most important contribution in the partition function was a product of a two-body encounter, let's say AB in one region of space, and another independent collision of two other particles, CD, somewhere else. Two separate two-body interactions were more frequent, more likely to occur than any single three-body encounter. Three-body terms came in at higher densities. So the people who knew about CI, or who were developing CI, they knew this kind of stuff from stat mech, and that's why they thought that maybe then the fact that the quadruple excitations, which are sort of trying to let two electrons over here do their dance, while another two electrons over here are doing their dance, that maybe the amplitude for that quadruple excitation would be related to the amplitude of these two electrons doing their dance, their double excitation, times these two electrons over here doing their separate dance, rather than four electrons all together. So that's what they had in mind. And let me just real briefly remind you how this partition function thing goes, because it's sort of a neat little derivation. What you do is you say what's called configurational contribution to the partition function would be the integral over all the coordinates of the n, let's say, atoms in your cluster of, say, argon, if it's an argon gas, of e to the minus potential over kt. That's partition function. You then say the potential is pairwise additive, v, jk summed over j and k. And then what you do is you say, oh, that exponential of that sum is nothing but a product of exponentials. This is just obvious algebra. But then what you do is you say, I'm going to write this exponential e to the minus v, let's say jk, that's the jkth interaction, as 1 plus parentheses e to the minus vjk over kt minus 1. The reason you want to do that is that the 1 is sort of the lead term, and the e to the minus vjk over kt minus 1 is like a deviation. That is, if the potential is very, very weak, then e to the minus vjk over kt minus 1 will be small, because the e to the minus will be approximately 1 minus the v over kt, so the 1 will cancel. So what you're doing here is you're going to build up something that's going to be expanded, and so you have this 1, which is the lead term, and then what you have is, so what I'm doing here is I'm taking this product of 1 plus e to the minus vjk over kt minus 1. So I'm taking it as 1 plus x, let's say, and I'm taking the product of that. So I'd have 1 plus x12 times 1 plus x13 plus 1 plus x23, et cetera, et cetera, et cetera. And I'm writing those out now, and the lead term would be the 1 times the 1 times the 1 times the 1 times the 1. That's the 1. Then the next term that would be linear in this deviation, so-called fluctuation thing, would involve 1 power of this e to the minus vjk over kt minus 1. So that's this next term here. Then the next term would be a 1 times a e to the minus 1 times another e to the minus 1. So that's this term here that would have 2 sums. And the bottom line then, and this is where you need to pay a little bit of attention, the lead term up there, the integral of the 1 integrated over all coordinates of all n particles, that just gives a volume of your system to the nth power, you know, because the integral over particle 1 gives v. The integral over particle 2 gives v. Particle 3 gives, so this is a v to the nth. And in the original partition function, there was 2 pi mkt over h squared to the 3 has v. There was a 1 over v to the nth that was in there that cancels this guy out. But then the lead term, so let me slow down here and just walk you through this a bit. This lead term that has the summation over j and k of its fluctuation integrated over all the particles, all those terms are identical because all the particles are identical in this argon gas. So there's really n times n minus 1 over 2 of them. That is, the sum over j and k is a sum over pairs. So there's n minus 1 over 2 such terms. And then the integral, therefore, can be over any one of them. So I just write here integral of e to the minus v of r, could be any pair, over kt minus 1. And this is what gives rise to what's called the first, it's called second virial coefficient, but it's the first correction to non-ideal gas behavior. But the thing I'd like you to notice about it is there's n squared of them, n minus 1 over 2. So this scales as number of particles squared. That's sort of like the number of collisions that can occur between pairs. But now here's where you really open the ears a little bit. The next term here that looks ugly, summation over I or j and k, whatever it is, and I and L, I guess it is, j and k and I and L. There's a sum over 4 things there. But there's 2 separate kinds of contributions there. If j and k, for example, are 2 particles over there, and I and L are 2 separate particles over there, then that gives rise to one contribution that scales as, let's see if I can find it here. Yeah, that scales like here as the number of particles to the 4th power. But then there's a possibility that j and k and I and L, you could have, for example, j is a particle here, k is a particle there, I is a particle also over there, and L is a particle over there. That is, like I could equal, for example, I could equal k, or I could equal j. And there's fewer of those interactions, but physically what that means is that particles j and k and I and L are not 4 separate particles. For example, I would equal k, or I would equal L. And physically what that means is that you would have 3 particles close together and then a 4th particle somewhere else. And there's fewer of those things. And so the bottom line is this is where the concept that two non-interacting, what are called uncoupled or disconnected pair interactions, where 2 are there and 2 are there, I, k, and j, L, is more important than a 3-body interaction, I, j, k, and j is equal to I, let's say, and an L over here. So from StatMech, they more or less knew that there are more of these independent pair interactions, and they would be more important because the ones that involve 3 at a time require 3 particles to be within the same volume element, so their potentials are, 1, 2, and 1, 3, and 2, 3 are all feeling one another, even if 4 is somewhere else in space. So to make that long story short, the StatMech point, the people who developed the coupled cluster theory, they were not surprised to see that these, or to postulate that the amplitudes of quadruple excitations could be well approximated by the products of the amplitudes of the separate independent double excitations. So that's the physical thing that's really motivating this e to the t weird way of writing the wave function. Now, there's also weird ways of going through the derivation of the equations, and I admit, because I think most of the people that I'm talking to in this audience are not that schooled in second quantization way of writing things, but let me just try to motivate you through the way that these things go. So you've already seen that the wave function, so we have basically the top equation here is h psi equals e psi, but psi is written as that exponential of t acting on your single determinant. So h x t phi equals e x t phi. If you then take that equation and multiply through on the left by e to the minus t, the point of that is on the right-hand side, then you just have e phi. And the reason that's an important thing is that you can then use that equation to derive an equation for e by just multiplying that equation through on the left by the single determinant. And so the energy would be written as phi, e to the minus t, h, e to the t phi. Phi is supposedly known to you. It's your single determinant. So if you could just find a way to deal with this e to the minus th, e to the t junk, you could evaluate the energy. Now, in coupled cluster theory, there's a thing called the Baker-Campbell-Hausdorff expansion that deals with operators like this. And this is something that is in second year graduate quantum mechanics classes in physics departments, where it's e to the a, b, e to the minus a. You know, we learn how to do expansions like that. The take-home lesson is these things can be written out. Yes, they're written out in terms of commutators and things, but they can be written out and handled. And the way you then generate equations for these t amplitudes, see in the t operator here, the unknown quantities were those t amplitudes for single or double, or if you're doing triple, also excitations. So the way that you do things is you take that Baker-Campbell-Hausdorff expansion, use it in the Schrodinger equation, as in this second line, multiply that equation through by a single excited determinant, or a doubly excited determinant, or a triply excited determinant, and in principle, you generate then a set of equations that can be used to solve for the amplitudes of the singly excited, doubly excited, triply excited. So if you're doing CCSDT, you would have to multiply through by single, double, and triple excited determinant, get a whole set of equations that would be enough in number to solve for the amplitudes of single, double, triple excited determinants, like the T-ij's, the T-ij-mn, the T-ijk, MNP, they could all be solved for. I think it's beyond a little bit the level of this lecture to go into the intricacies of the coupled cluster theory, but I just want to let you know that these equations are nonlinear. You can see that the equations will involve products of t times t times t times t. They're quartic equations. They have to be solved in a very tricky way that is not like a simple matrix eigenvalue equation like in CI, where you have matrix times CI vector equals E CI vector. So they're nonlinear equations, but the assumption, the physical assumption in coupled cluster theory that the higher order pair correlations, quadruple, six-fold excitation, and so forth, can be well approximated by TT and by TTT, actually physically is important and wasn't a useful breakthrough for coupled cluster theory people. The price they paid is the equations that they end up with that they have to solve are highly nonlinear equations. But people have developed these kinds of methodologies, and they now routinely, or not routinely, but they can solve these things. There is one thing I'd like to say before closing this rather complicated transparency. I think a lot of people these days are used to the thing CCSD parentheses T. And what that is doing is people realize that when they did calculations using coupled cluster theory, including single excitations, double, and triple, the cost of doing these equations that arise in this bottom line here from the triple excitations it was very, very expensive. So they said, is there some way we could approximate the amplitudes of the triple excitations by perturbation theory? So they made some approximate development where they said, we will properly solve the single and double excitation equations, but for the triple excitations, we won't solve this expensive thing. We'll make some approximation to it. That's what CCSD parentheses T is about. So let me just summarize a little bit of what we've been talking about so far and remind you of just some scalings and things like that. We talked about basis sets long ago, not even in this session that we're talking about, and obviously we talked about basis sets in the valence region, polarization functions, diffuse functions, and so forth. And you should, I think, be familiar with that. But the thing to be careful about is to remember that these basis function sizes, as they grow, the scaling of cost of calculations of things that you want to do are often going to scale, of course, as basis set cubed. That would be solving the Fock matrix problems. Basis set to the fourth, number of 2 electron integrals. Basis set to the fifth, like in Møller-Plesset perturbation theory 2. Coupled cluster theories even scale worse than the basis set to the fifth. Integral transformations, basis set to the fifth. We learned about electron correlation. We have to include it if we want to get accurate energies because it's an important number. Remember the graph that I made of how big is the fluctuation potential, the difference between the Hartree-Fock and the real potential? It was huge. So the electron interaction is a strong potential that has to be treated usually to get chemically reasonable accuracies. And we talked about CI, Møller-Plesset, coupled cluster. Haven't yet talked about DFT, but will, and MCSCF. We warned you about single determinant wave functions being a problem, and keep in mind the highly nonlinear scaling of the computational cost with the size of the MO basis. And just to remind you one last time, this is nearly the end of this session here on coupled cluster theory, but I'm just trying to review a little bit about scaling. In all of these methods, one thing that is a problem is you have these two electron integrals over basis functions. They're of the order of m to the fourth of them. You can't escape that. Now, I want to make one side comment here too. In the literature these days, we hear a lot about the word linear scaling. And that's something that we haven't talked about yet, but I just want to briefly mention, because you think, does that mean people are smarter these days and they're coming up with algorithms that don't have this m to the fourth and m cubed and m to the fifth? Not really, because the linear scaling that they're talking about, they're usually talking about problems where they're interested in very large systems. For example, let's say a fairly long conjugated polyene. And the idea basically is that if you have on this part of the polyene some basis functions on these carbons and then basis functions on neighboring carbons and so forth, you would think that somehow you should be able to develop a theory that as you make that carbon chain, say 20, then 30, then 50 units long, that the basis functions that are at that end of the molecule interacting with basis functions on this end of the molecule, because the atomic basis functions are fairly localized, that you could ignore their interactions and stuff. And that's basically what they do in linear scaling. So what we're talking about when we say linear scaling is if you decided you want to say a polarized valence double zeta basis set on each carbon atom, it is true that people are developing methods as you go from 20 to 30 to 40 to 50 carbons in a polyene, that the total time of the calculation will not scale, let's say, as the total number of basis functions to the fourth. And the way they do that is they realize that, for example, in these two electron integrals, these chi things, if you have a basis function that's on this carbon atom as chi A, and chi B happens to be a basis function that's way over there, and chi C is one that's here, and chi D is one that's over there, if they're geometrically distant from one another, they introduce approximations. The crudest approximations are if things are far enough apart, they ignore them. They don't do a calculation. If things are moderately close, they approximate some of these interactions. Because remember, these integrals here that we have, the physical meaning of this, chi A for electron 1, chi B for electron 2, chi C for electron 1, chi D for electron 2, that should be thought of as sort of the Coulombic interaction, because G is 1 over R1, 2, of a charge density for electron 1 that's the product of chi A times chi C, interacting with a charge density for electron 2 that's chi B, chi D. So if chi A, chi C overlap in some region of space, you think of that being a little localized electron density. And then if chi B, chi D overlap somewhere over here, if these things are fairly far apart from one another, you can approximate just by simple electrostatic approximations of how big is this charge density, how big is that, and how far apart are they. So they've introduced various either ignoring integrals or approximating integrals by electrostatic interactions rather than doing the real integral honestly. And people now do have linear scaling methodologies that scale linearly as you go to larger and larger systems. What they don't have, and this is where you don't want to be fooled, is if you're doing a calculation, say, on ethylene, a single olefin, and you put in a basis set, and then you double the size of the basis set, and you double it again, it'll still be m to the fourth. So every time you double, you're going to get 2, 4, 8, 16-fold increase in the number of these integrals. So the linear scaling is not effective when you're talking about putting basis functions in the same region of space. It is effective when you're talking about a given basis set and then a molecule that's extended. By ignoring a lot of these integrals, people have gotten so that as a function of how many fragments in the system the difficulty will scale linearly. So it's a little bit of a red herring, in my opinion, this phraseology about linear scaling. So number of integrals, m to the fourth. To solve the Fock problem, you know, if Fock matrix times MO coefficient equal orbital energy overlap MO coefficient, m cubed, because the dimension of the Fock matrix is m by m, and to find all the eigenvalues of any matrix of dimension m requires of the order of m cubed operation. To calculate the two electron integrals in the MO basis, not in the AO basis, but in the MO, to transform the AO integrals to the MO integrals, there's m to the fourth of these MO integrals, but you need m to the fifth transformation steps to do this transformation, like I talked about a couple of times ago. If you're solving like in CI or MCSCF, the secular equation that's over the, to get these so-called configuration amplitude coefficients, the number of configurations, NC, in this matrix determines the size of that matrix, NC by NC. You're going to require NC squared operations to get one state energy. If you want all the state energies, it's going to be NC cubed. MP2, as I mentioned, scales as the number of basis functions to the fifth power. Couple cluster theory is even more severe. It depends on what level, but m to the fifth, sixth, seventh, and higher can appear in couple cluster theory. So generally, couple cluster is the most expensive, Hartree-Fock's the cheapest. And things like MP2 are in between. Okay, that's the end of that baby.